Alright, question 8. Let S be a cube. We get S with two planes parallel to two opposite faces, with three planes parallel to two other opposite faces, and with four planes parallel to the remaining faces. So S is divided into, we have 24 parallelepipeds, we have 60 parallelepipeds, we have 9 parallelepipeds, and we have 12 parallelepipeds. So the first thing about this question is that this question came in the MENG exam of 2020 and there was no correct answer. Okay, but it now came in 2021 with the correct answer. So be very vigilant whenever you're solving questions and there is no correct answer. Always strive to get the correct answer, not necessarily getting a letter, just get the correct answer. So if there is no answer, actually know that okay, there is no answer, but this is the correct answer. Okay, so we are going to first of all indicate a cube, and then we try to section the cube using those planes as we're being told in the question. So practically, when I was teaching last year, I actually did it practically in class. So we bought a Maggi cube. Okay, we bought a Maggi cube, and then now we used a razor blade, and then we sectioned it, and when we counted the number of parallelepipeds that were involved, and we had the correct answer. So this is what we are going to do. Let's begin with the first statement. We get S with two planes parallel to two opposite faces. So we are going to consider the face, this face here, meaning the left and the right face. Okay, just if possible, right, just hold a Maggi cube and follow up, or a box of chalk, or any box that has a cube-like structure. So we are going to use the face that is, we are going to consider the two faces, the two parallel faces. Our first consideration is the two parallel faces that are to the left and to the right. Okay, so we have this face here and the other face that is to the left. So if a plane is parallel to these two faces, then it must be in the same orientation, in the same direction as those two faces. So I'm going to use these two planes. Okay, so here is the first plane and here is the second plane. All right, now the next statement is saying that we now take three planes and we get the cube with three planes parallel to two other opposite faces. So we are now going to take the face at the top and the face at the bottom. Remember, there are 6 faces, so we have already used 2 already. We are left with 4, and we are using the faces in pairs. So we are now going to take the face at the top here and the face at the bottom. All right, so the face at the top and the face at the bottom are horizontal faces. Therefore means that the planes are supposed to be horizontal. So we kept using these red planes, 3 of them. So we have, so those are the 3 horizontal planes. Okay, and lastly, we now have to get S with 4 planes parallel to the remaining faces. So the remaining faces are now the front face and the back face. The front face and the back face are vertical faces. Okay, they are vertical faces. All right, so we are going to use vertical planes. So there are 4 planes that we are going to use. So we have the first plane, the second, the third, and the fourth. Now we have to count and know the number of parallelepipeds that exist. What is first of all a parallelepiped? It's simply a figure that looks like this. So it is kind of a parallelogram, but in 3 dimensions. All right, so it therefore means that this is a parallelepiped, even this is a parallelepiped, this is a parallelepiped, this is a parallelepiped. All these figures here that look like parallelograms, okay, they're in 3D, they are parallelepipeds. So if you want to count the total number, all right, we are going to just use the formula. We count here you have 1, 2, 3, 4, 5. We count vertically, since we're using vertical planes here, we have 1, 2, 3, 4, and then we now count horizontally. We have 1, 2, 3. So we multiply all of them, and then we get how many? 60 parallelepipeds. So to be more practical, you can take a Maggi cube, right, and then you try to section it. You're going to have some small pieces. If you respect all of these sectionings, you're going to have small pieces. When you count them, you're going to have 60 in total. So B is the correct answer. Okay, question 9 is a little bit long. it reads the polynomial x to the power 5 plus ax plus 1, option A, has never real zeros. Option B has at least one real zero for each a in the set of real numbers. Option C, we cannot tell if it has real zeros because the degree is too high. And option D, none of the above. Okay, so there are two methods that are actually used when solving these questions. Okay, and I'm going to just use one method to make the video a little bit shorter, because I never wanted to make the video be longer. So I'm going to use one method, and that method is very useful in other questions, and it's a little bit shorter. All right, so what we are going to be doing is that we are first of all going to let f of x to be the polynomial given x to the power 5 plus ax plus 1, and we specify that a is a real number. Now we are going to use what we call the Descartes rule of signs. Now this Descartes rule of signs says that what? It says that the number of positive real solutions to an or to a polynomial is equal to the number of sign changes in the polynomial from one variable, from one term to another. This is what I'm saying. F of x is equal to x to the power 5 plus ax plus 1. So we are going to consider separate cases of a. Since a is a real number, it's going to be it's going to be preferable that we take three cases. We first of all make a to be 0, we take a to be greater than 0 and a to be less than 0. We are choosing 0 because 0 is neutral. Okay, so we take a to be 0, our f of x becomes x to the power 5 plus 1. Automatically we can deduce that there is no sign change, because you see in most form we are just taking the sign changes. The sign in front of x to the power 5 is a positive sign. Now when you go to the next step, it's still a positive sign, so there is no sign change. And since there is no sign change in f of x itself, then there is no positive real solution. Now let us now look for the negative real solutions. How many of them exist? So the number of negative real solutions are the number of sign changes in f of negative x. Follow keenly. So we are going to find f of negative x, and then you clearly see that how many sign changes are here? There is one sign change from negative to positive. So it therefore means that there is one negative real solution, because there is one sign change in f of negative x. So in conclusion, there is no positive real solution and there is one negative real solution. When we add them together, we have in total one real solution, and that one real solution is negative. So you see that for a equal to 0, there is only one real solution, and it is negative. And clearly we can know that that negative solution is negative 1, because f of negative 1 is 0. Okay, and clearly it is negative. So we have one real solution, which is indeed negative, because of the conclusion from the Descartes rule of signs. Now let's take the second condition, the second scenario, where we now take all positive values of a. The first case, we took a to be 0. Now I cannot take a to be 1 or a to be 2. I'm just going to take, I'm going to generalize it. So I take now all positive values of a. My f of x still becomes x to the power 5 plus ax plus 1, and I specify that in that case a is greater than 0. Okay, so let us find the number of positive real solutions. Now we can identify that there is no sign change, right? So there is no positive real solution. No sign change because it moves from here positive to positive. If this a was negative, then everything here is going to be negative. But since a is positive and there is a positive sign here, then the resulting sign is positive. So we have positive to positive to positive, no sign change. In conclusion, no positive real solution. Now we go ahead to get f of negative x. That is replacing x with negative x, taking it to the power 5, and then replacing x here with negative x as well. How many sign changes are here? There is only one sign change. Negative to negative is no sign change, but negative to positive is one sign change. So since there is one sign change, then what's the conclusion? There is one negative real solution, because this one sign change is for f of negative x. So what can we conclude? How many real solutions are there? We have one real solution, which is still negative. All right, so for all positive values of a, there is only one real solution, and that real solution is negative. So for a equal to 0, we have one real solution, which is negative. For a greater than 0, we also have one real solution, which is also negative. Now let us take the last case when a is less than 0. So when a is less than 0, we have f of x to be x to the power 5 plus ax plus 1, and we specify that a is less than 0. But if I actually explain the sign changes here, you might be lost. Okay, so I'm going to specify that, okay, since a is less than 0, it means it is negative. Therefore, it should be what? Maybe I can replace it with negative b, where the b there is a positive number. All right, negative times positive is negative. So it means that my f of x will be x to the power 5 minus bx plus 1. The b here is positive because there's a negative sign attached to it, which is actually a. All right, now let us now look for our number of positive real solutions and negative real solutions. So how many sign changes are here in f of x? There are two sign changes. From positive to negative is one sign change. From negative to positive is another sign change. So it means that there are two positive real solutions because there are two sign changes in f of x. Now let us now look for f of negative x. We get this. Now how many sign changes are here? We have negative to positive is one sign change. Positive to positive is no sign change. So there is one sign change here, therefore one negative real solution. So when we add the two positive and the one negative, we have what? Three real solutions, two positive and one negative. So in conclusion, we can now conclude that what? When a is equal to 0, there was one real solution. When a was greater than 0, there was one real solution. Therefore, when a is greater or equal to 0, there is one real solution after combining the two situations here. And then now when a is less than 0, how many solutions do we have? We have three real solutions. So what's our conclusion? We are concluding now that it has at least one real solution for each value of a. You see that at least one means 1 and above. For it to be 1, your a must be either greater than 0 or equal to 0. Now for it to be greater than 1, your a has to be less than 0, since we have 3 in that case. So option B is correct. Now the other method which I usually do is actually plotting the graph and seeing how many times the graph gets the x-axis. But it might be a little bit longer and complicated for some of us. But if you master this method very well, since you are not actually finding the numerical values of those solutions and you are finding just a number of solutions, then the discard rule of signs will be better. So the answer is B.